let's get started. Um, okay, so we have finished lectures 1 through 4. So if you're still sticking around, good for you. This was already very hard to get to this point in time. So you guys are doing great so far. And that being said, there are definitely some like major problems in the proofs that people are writing, and this is not like a personal attack on anyone. This is just a testament to the fact that proofs are really, really hard. So, um, these are just some reminders. So, and this one is sounds obvious, right? Don't make assumptions. Um, but it's really hard to not make assumptions. And I got my ass beat in my first few proofreading courses. I made assumptions all the time, and I had to, really figure out stuff. But always keep this at the forefront of your mind. You want to develop this kind of itch in the back of your brain that, hey, is this really something I can assume, or maybe not? Um, so don't make unfounded assumptions, and it can be really trivial stuff sometimes that you are not allowed to assume. So feel free to ask like at any point, because usually there's always someone active in the Discord who will want to tell you yes or no. Um, okay. Use English effectively. So yeah, there's definitely a lot of proofs I've been seeing where if you said that sentence in real life, people would look at you a little funny. Um, and yeah, also stop using logical symbols in proofs. You basically never want any logical symbols in your proofs. Maybe in like backslash in is okay. Um, but you want your proofs to basically look like very coherent English paragraphs. And maybe you're annoyed because you just finished expos and you're kind of tired of that. But it is writing. So try to write as beautiful as of sentences as you can. And the last thing, and these are, yeah, again, or in order of importance, don't write War and Peace. If you don't know what that is, it is a very, very long book. So I was taking chemistry over the summer, and my teacher was maybe a little bit unhinged, and he like threw out and ripped up some kid's test because uh he had written on the back as well when trying to explain his answer. And he just screamed at us to not write War and Peace, and I didn't know what it was. But I don't think I'm ever going to forget what it was. I don't actually think in this year's batch of submissions many people are writing too much. But I do want you to keep in mind that every single word should be necessary. And that will make your English coherent. That will make your proofs very good. But obviously, if something is necessary to be said, then don't cut it out. Okay. So sorry for giving you the bad kind of lecture before the lecture. Let's actually do the fun stuff now. Graphic illustrations, where to find them. So this is a crash course on graph theory. So there are no illustrations. I just thought it was a funny title. Although I will be drawing some pictures later on to help with intuition. So, okay, let's define a basic graph. So it's a pair of vertices, a set of vertices, and a set of edges. So V is an arbitrary finite set. So just a quick note on this. I will only ever in my entire life care about finite graphs. I will never care about infinite graphs because they're weird and I don't like them. Um, sometimes people may try to make you look at infinite graphs, but you should tell them no, I don't do that, and you'll have a much better life. Okay. So, and normally V will be like just the first like n numbers if n is the number of vertices in the graph. Okay. Now the edge set is going to be a subset of V times V. So that's just saying that the edges are just pairs of vertices. Because this is Cartesian product. Okay, and of course elements of V are vertices, elements of E are edges. Okay, so this phrase basic graph is something I introduced like 20 minutes ago into the lecture notes. Um, we computer scientists have this problem where they want graph to mean something and they want graph to mean something else, and so that's not good. We can't overload the phrase graph. So I refer to this as basic graph, which is obviously lengthier than the word graph, and that is because we basically don't really want to use this definition most of the time. We want something more specific, and we'll define that very shortly. Okay, so an undirected graph is one where every AB that's an edge implies that BA is also an edge. Okay. So what that is saying is that uh so let me draw a picture. That will probably help. Okay. So let's draw a very basic graph. We have just two vertices here. So let's say we have the edge 1, 2, right? So we would draw it like this. And in our basic graph structure, this would be like uh, a directed graph, right? The opposite of an undirected graph. So edges have directions. It matters which thing comes first in the pair. But when I say, okay, now we're talking about undirected graphs, so the presence of this edge 1, 2 implies the presence of the edge 2, 1. And so we always have this kind of thing going on. And then at this point, it's just prudent to say, okay, let's forget about drawing both edges every single time. We'll just draw it like this, right? So this is what you should think of when you see an when you hear this term undirected graph. Um, okay. So there's a convention here, which is that when we talk about undirected graphs, AB, the pair AB is the same as the pair BA. It's just pragmatic. It's definitely an abuse of to some extent because these are not equal objects for obvious reasons. But it just makes our lives easier to do this, so we are going to do that. A self loop is what it sounds like. It's an edge that goes from a vertex to itself. And then finally, the definition of graph that we're going to use for the rest of this lecture is an undirected graph with no self loops. So every edge is going to imply the existence of an edge in the reverse direction, and it will never start and end at the same vertex. Everything okay so far? Yes, good. Okay. So now let's do some examples. So okay, like G equal VE. V is the first 5 numbers. And okay, we have this stupid looking thing, so let's look at it carefully. 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1. So okay, if we want to draw this, we'd have just this. Okay, so we have this nice little loop here. Okay, next example. Okay, these again the same set, so we have 5 vertices. And now we have the edge set is every pair of vertices where I is not equal to j. Okay, so now I'm just going to modify the previous graph. So everything is connected to something. So every pair of vertices is connected as long as the pair is not like a vertex in itself. So I literally just go connect everything. And I've just put the star in the middle, and that is enough. And this graph is known as K5. So this is we call this the connected graph on 5 vertices. And of course you can have the connected graph on 2, 3, 4, 5, whatever number of vertices you want. It's just going to look like this big mess. Yeah, it does look like a pentagram. Okay. Okay, again the same vertex set. This time we have fewer edges, only 4. We connect consecutive vertices together, so okay. This is known as P5, the path graph, with 5 vertices. And it will be very clear why we call it a path graph, although maybe it's kind of intuitive to begin with. And okay, first 4 vertices, and we connect 1 to I for each I from 2 to 4. It might have been easier to write this out without this set builder notation, but whatever. So we have 1, let's drop that, 2, 3, 4. And this is known as a claw graph. And claw graphs are actually pretty interesting. Wait, sorry. Yeah. So there's a claw. This is interesting because it turns out graph theory does interesting things, specifically regarding graphs that have certain number of subgraphs that look like claws. Adam, am I recording? I am recording. That's a good question, but it's not a good question to ask this far into the lecture. Very scary. Um, I do see a lot of pings. What's going on here? Oh, I see. Yeah, so someone asked about posting the recording. That's fine. Cool. Anyways. Uh, okay, so yeah, these are just some examples. These are kind of useful to always hold in the back of your head because whenever you start thinking about properties of graphs, it's really helpful to have these examples and just go ahead and try these out and see what happens. Okay. Um, so okay, yeah, so path is very strongly related to the path graph right here. It's a sequence of unique vertices of v1 through vn, such that each pair and consecutive vertices are connected. By connected, I just mean there's an edge directly between them. Um, so obviously there's like a lot of paths inside of this graph here. So one path in here would be 1, 3, 4. And in fact, I can pick any sequence of unique vertices inside of this graph and they will form a path because every consecutive pair of vertices will be connected. This is obviously the simplest graph with the path of length 5, and that's why it's called P5. So you get the point. Okay, so a cycle in a graph is also a path, but it has the restriction that the first and last vertices have to be connected. So, for example, 1, 3, 4 is again a cycle now because 1 and 4 are also connected. Okay, and a graph which doesn't have a cycle is called acyclic. And now let me introduce one more type of graph. Actually, two more because I didn't introduce star graphs. So this is called the star graph on. Okay, wait. I always forget how many vertices the star graph has. Okay, so this is called S3, which is kind of messed up because it has 4 vertices. But the point is that this looks like a star because you could do like this kind of thing in general. So this oh sorry. So this one is S4. Get it? It looks like whatever. But yeah, the number is just how many leaves there are here. And the last one is let's do C5. So this is called the cycle graph on 5 vertices. So actually we had it before, but I guess I destroyed it to make K5. 4, 5, boom. And the cycle graph on 5 vertices is obviously called that because it is the simplest graph which has a cycle on 5 vertices. So there you go. Here's a bunch of things to commit to memory. Hopefully the names are good enough to try and remember them. Okay, and yes, so talking about cycles a little bit more, if a graph doesn't have one, it's acyclic. So this graph has no cycles. This graph has many, many cycles. This graph has, these two graphs have no cycles, and this has exactly 1 cycle. Oh, and I added something very recently to this, which is that oh, it didn't get compiled, my change. Okay, well anyways, so another restriction on cycles is that they have to have at least 3 vertices. So the point is that you need that because for example, this is not a cycle. It technically looks like a cycle because 2 and 3 are connected and 3 and 2 are connected, but it's not a cycle because it doesn't really like fit our definition of cycle. Anyways, so yeah, so you need at least 3 vertices to form a cycle. Okay. Any questions? I know I'm throwing a lot of definitions, so it's definitely gonna help a lot to go through the homework and just keep referring to these definitions. Hopefully that will be enough to commit it to your memory. We chilling. Okay, very good. A graph is connected if for any 2 vertices there's a path between them. So this matches our intuition of the word connected. So for example, if I gave you a graph that looked like this, you would say, ah, this graph doesn't look very connected because I can just kind of split it apart. Notice that there's not always an easy way to tell visually if a graph is connected or not because the edges could be all on top of each other or something, and it's not clear if every pair truly has a path between them. But of course, if you're a computer scientist, then you would know that there's a very nice algorithm to see if a graph is connected or not, which we will talk about in a moment. So now our first really nice definition here in graph theory, here's a tree. So a tree is a connected acyclic graph. Okay. So there's two important parts. It needs to be connected and it needs to be acyclic. And these are kind of I guess contending in some sense. So being connected requires having enough edges in some sense, right? So I need to have enough edges where I have a way to get between my vertices. So for example, if I had only one edge and a million vertices, there's absolutely no way my graph can be connected. And similarly, being acyclic requires that you don't have too many edges. Because if you throw in too many edges, then eventually you're going to accidentally add in a cycle. So these two properties being contending makes trees kind of interesting. It actually forces them to be a very specific way. Okay, so let's take a look. Are any of these trees? So this is not a tree because it's not connected. This is a tree because there's no cycles and it's connected. This is also a tree for the same reason. This is not a tree. It has a cycle. This is a tree. It's connected. It can go between any pair of vertices and there's no cycles. And this is not a tree because it has a million cycles. Okay. So trees are these guys. Okay. Let's see. Yeah, let's talk about some intuition on trees now. New one. Okay, so uh, so in computer science we have this nice thing called a BFS. So BFS is a breadth first search, and the point is that you're kind of iterating through the graph in a way where you're expanding the set of vertices you've seen so far in kind of waves. So another nice thing about trees is that you can do something called rooting them. So you can pick an arbitrary vertex, and then you can say this is the root. And then now what you can do is you can look at all of its neighbors. So what I'm showing you so far is only the set of vertices that we sort of explored at this point. So I look at all of its neighbors, and this is an easy thing to do in most representations of graphs. And I say, okay, it has 3 neighbors. And now I say, okay, I've expanded my BFS by 1 layer. And now what I do is I just keep repeating that procedure, but now with these 3 guys simultaneously. I say, okay, this guy has 2 neighbors. This guy has no more neighbors that we haven't seen, and this guy has 1 more. And so I'm expanding in waves like this. So, specifically for a tree, this process must hit every single vertex, and that's because trees have to be connected, and so there must be a path from this guy to every vertex. So that path must appear somewhere along here, and so eventually I must hit it. And also, because it's a tree, I will never hit the same vertex twice, as long as I ignore things that were directly before me. And that's because there must not be any cycle. So for example, this is impossible. This is impossible because that would mean we have a cycle. So anyways, so I could do this BFS, and that would allow me to check if my graph is a tree, because for example, I should never see this kind of thing, or I don't know, this kind of thing, whatever. And I should also end up seeing every single vertex. As long as I do that, then I have a tree. So whenever you think of trees, you can just kind of think of them like this, rooting them, and then every guy has some set of children, and that should be good visualization for trees. Whereas in comparison, graphs can look kind of bad. So that's kind of like comparing finite sets versus infinite sets. Finite sets are a lot easier to think about. Can 2 roots converge? So you only have 1 root in a tree usually. I don't think I know I've ever heard of having 2 roots. What would you mean by converge exactly here? Maybe you're referring to the process of doing this BFS in some way. Like two nodes connected to the same node, then from that node splitting off into a standard tree. Um, Sorry, I'm not sure I understand the question, but how about we talk a little bit after class? Just in the interest of saving. All right, so let's continue. Um, okay, some more definitions. Enjoy. The degree of a vertex is the number of vertices it is connected to, and specifically, if a vertex has degree 1, it is called a leaf. So here, this vertex has degree 3 because it's connected to 3 things. This vertex has degree 3 as well. It's connected to 3 things. Its parent and its 2 children, like we call it in computer science. This guy has degree 1, so he's a leaf. Degree 2, degree 1, another leaf. Degree 2, degree 1, another leaf. And degree 1, another leaf. So just count the number of edges touching something, and that's the degree. Okay. And now we have a big one here. This is something you should definitely remember. This is known as the well ordering principle, WOP for short. You can just call it WOP. We'll know what you're talking about. And it states that every non-empty set of positive integers contains a least element. So we used something kind of similar to this before, but this is the exact statement that we're going to use here. And we're going to use it very shortly, and it'll be nice seeing this kind of fundamental fact coming into use in graph theory here. Okay. And there's also something called the well ordering theorem, and I added this note because I actually called it this by accident, and then I realized that, oh, this is something completely different. So this states that every set has a well ordering, which is a kind of shocking statement, but you probably don't know what that means at this point in time, so we'll ignore it. But we will discuss it later when we talk about relations. And anyway, so WOP itself, it sounds very simple, right? If you have positive integers, then you have a least element. So this sounds like really obvious, like Adam, why are you telling us this? You can just take the min because the min is somewhere between 1 and some number out there. But it turns out this is equivalent to axiom of choice. And that's very scary because axiom of choice leads to some very frightening consequences in some fields of math. So that's why we sometimes talk about math with the axiom of choice and math without the axiom of choice. Okay. So anyways, strange things aside, let's actually prove our first statement about graphs. Um, so proposition 5.15, every tree has at least 2 leaves. Okay. So let's think about the intuition here, right? So um does this graph have at least 2 leaves? And I hope everyone agrees that the answer is yes, because there are 1, 2, 3, 4 leaves. Okay. So when you're trying to prove something, right, you want to kind of play this game like flip-flopping between proving that it's possible, proving that's true, or finding a counterexample. And kind of going between the two has this nice benefit of improving your intuition for both sides. So, let's actually try to make a graph that doesn't have at least 2 leaves. And so we notice that something interesting goes on as soon as we split off, right? Like this guy has 2 children, right? So we split off, and I noticed that as soon as you split off, you kind of have to end somewhere. So if I split off once, then I get at least 1 tree off to the left here, and at least one leaf off to the left, and at least 1 leaf off to the right. So I'm kind of not allowed to even split off because that will give me at least 2 leaves. So finding a counterexample means I can't split off. So okay, what happens if I don't split off? So okay, I only have 1 choice. I have to draw this. And then I can't split off, so I keep going. And so I just basically have a path graph, right? If I'm not splitting off. And so when I have a path graph, then the bad thing is now the root is also a leaf. So So this is just completely impossible, it seems. Uh, if I do split off, then I'll introduce at least two leaves. If I don't split off, then the root will become a leaf. So it seems like no matter what I do, I'm gonna have at least two leaves. Um, the unfortunate thing here is that uh, when I look at this, I do get the intuition, but this actually has nothing to do with how we prove it. Proving it is actually rather challenging. So this solution will appear completely let's say unintuitive as to how you would think of this, but nevertheless, I think I'll make it make sense. Oops. Right. So let's have a shot. So of course we begin by instantiating a tree because we're talking about every tree. Now we construct this set, and so as soon as you construct this set and you think WAP, you may see where this is going, but let's proceed anyways. Uh, so let S be the set of lengths of paths in G. So now S is a set of integers, and it's bounded above by the size of the graph, right? You can't have a path that's longer, that has more vertices than number of vertices in the graph, because paths require that the sequence is only unique elements. So let me just show you this. It's a sequence of unique vertices. So a path can't be longer than the size of the vertex set. So S is definitely bounded above by this. And now we use WAP. We actually use it the other way around. We just flip some signs. And so now, because it's bounded above, it must have a maximum. So there has to be a path length which is of the longest length possible in this graph. Okay, so you can kind of think like, okay, if I have this tree, right, on the left, then the longest path is this guy, right, like this. And now you kind of see where this is going. We actually start and end in leaves, right? We start and end in leaves. And now I'm going to show that these two guys have to be leaves by taking the longest path here. So the problem is I don't have the longest path right now. I have the length of the longest path. So now we just show that obviously if this path length exists, then there is some path. And now I get to instantiate my path. And now I have two vertices, v1, vm, that are going to be the vertices I'm trying to show are leaves. And the important thing is that this is the longest path. This is very important in actually doing the proof. So now let S be some neighbor of v1. The point is that we want to show that v1 has only one neighbor. Okay, so now we do something again not super intuitive, and this is kind of the nature of some proofs. The intuition can be totally there. Visually, this makes a ton of sense, I think, to say like, okay, there are definitely two leaves here. If you attach some S, then this would create a contradiction in some sense, because that would create a longer path, right? And this one was already the longest, so this guy's only connected to one thing. But to formalize it, you need to be a little tricky. So what we say is, okay, consider this sequence, right? It has this. And I have a typo here, but just ignore that. So this can't be a path. And that's because if it were a path, then we have a path that is longer than the longest path. That's a contradiction. And so the only way to make this not a path, so there's actually two ways to make this not a path. Either S is not connected to V1, but we assume that it is, or S is equal to something else in here. So that would mean that this sequence is not consisting of totally unique vertices. And so it's not totally unique, so S is equal to some VI. Okay, which VI is the question? Well, obviously, if it was some VI that was further down, then you have a cycle, right? So if S was equal to like V3, then V1, V2, V3 would be a cycle, and that's not possible because G is a graph, right? Sorry, G is a tree. G is a tree, so it's acyclic. So the only possibility is that S is actually equal to V2. So if this guy was connected to some vertex, it has to actually be just this is S. And that means that since there's only one option, this guy is a leaf. That's a result. So proving that this is a leaf is actually a very arduous thing. You have to show that its only possible neighbor is this guy, because if it wasn't, then there would be a longer path. Okay. So, do yeah. So this proof also works the same way on VM. So this guy's also a leaf, and so our tree has at least two leaves. Okay. So we found our two leaves, so we're done. We instantiated a general tree, and we found two leaves. And also note that two leaves might be the minimum because if you have a path graph, you have only two leaves. Okay. So does that proof make sense to anyone? To everyone. I'm actually going to give you just a moment to try and digest the proof. Go ahead and stare at it. Let me know if there are any questions. Okay, I'm going to assume people have enough time to digest this. Um, so now that this proof totally makes sense to you, can someone tell me why this proof is wrong? Ha! I tricked you. Yeah, Max, this is a very terrible prank I've played on the class. So I'm gonna make your lives a little easier. I'm gonna tell you that this statement, first of all, is not even true. And it's not true, and Rohan's very unhappy with this. Okay, so this is not true in a very similar way to the daikon radish one. Daikon radish. Um this is not true in a very similar way. So okay, so can anyone tell me why this wouldn't be true, and the reason is just very, very similar to that. Hey, I am gonna spoil it now. It's that it doesn't work for n equals 1, right? So the inductive step in my fake proof from before didn't work when n equals 1, and same thing is true here. There aren't even two vertices to be leaves when you have only one vertex. So if this was my entire graph, we have one leaf, and that's kind of it. There's nothing more to be done. So now, knowing that this is a problem, can anyone spot where I actually make the mistake? My call ends in 10 minutes, yet again. How sad. There doesn't have to be a path from V1 to VI. Yeah. So, yeah, so first of all, um, I assume that there is even such an S, right? So I've instantiated an S that has this property, but there might not be any such variable. So, um, yeah, so this is just complete nonsense, right? Like V2 doesn't have to exist. Uh, this could just be all completely wrong, right? And VM doesn't exist either, or rather, it is just V1. So how do I know that they're two different leaves, right? So yeah, the mistake is kind of everywhere. It just kind of assumes that V1 is far away from VM, and so always be careful of these kind of ellipses because what is actually there and are these even different in the first place. So good for you guys finding that. Um, of course we just amend this and we say every tree with at least two vertices has at least two leaves, and then we're fine. This is the only problem. Okay. Every tree with n vertices has n minus 1 edges. So, uh, my plan for going over this proof is basically, let's build some intuition. Let's do this a little slow. Another canvas. So, if you are far enough along in your computer science career, you will know about something known as disjoint set union. And the point, or rather the process going on in disjoint set union, is you have these buckets. You have these buckets, and they might have some interesting properties going along inside of them. So uh, maybe when we combine buckets, something interesting happens. But for our purposes, we're just going to be thinking about the part of the main process, which is just combining buckets. So in disjoint set union, we find a fast way to do the following process. Um, we have a way to quickly join things together. So maybe I want to join buckets 1 and 3 together. And then later on, I want to join buckets 3 and 5 together. And then the second thing is that I can quickly find if two numbers are in the same joined group, I guess. So I can find very quickly, are 1 and 5 currently in the same group? And at any point in time, I can interleave these queries of are these guys together and joining things. I can actually be I can do some very nice things with that property. Okay, so but for our purposes, we actually just care about thinking of a graph and thinking of what happens when we add edges. And so I'll give you the notion of a connected component, and that is a connected component is exactly the same notion as our groups right now, which is that this is a connected component, and that is the case because everything I messed up my line. But everything inside of the connected component pairwise can reach each other, and anything outside of the connected component can absolutely not reach it. So we have let me try that again. One connected component, two, three, four connected components at this point in time. So notice that if I add an edge between two things that are currently in the same connected component, so if I did this, right, then I would definitely create a cycle because those two vertices are in the same connected component, so there's already a path between them. And by adding that edge, then I've put the last nail in the coffin, which is I've connected the first and last thing in the path, and so now I have a cycle. So I can never connect two things that are in the same connected component. So when I do add an edge from my tree, I can't do that. I have to connect two different connected components. And so maybe I would do something like this. And the point is, if I connect two different connected components, then I decrease the number of connected components by exactly one, right? So now 2 and 4 are no longer two different connected components. After joining them, they're only one connected component. And every time I do this, I just decrease the number of connected components by one. And in the end, I need to have exactly one connected component. So I start from n connected components, and I need to go to one connected component, right? And then one edge corresponds with uh, decreasing uh, one connected component. Right? So that means that in a tree, I have the intuition that I should have n minus 1 edges. Because if I added them in one by one, I should decrease my number of connected components from n to 1. Okay, does this intuition make sense to everyone? I really hope this is clear. But yeah, I just keep joining things until I have one big group, and I did that n minus 1 times. It's okay with everyone? Continue. So right, so yeah, how do we prove this? So uh this is not an easy thing to prove. And the problem is kind of that I've given you this intuition of counting the number of connected components, but kind of similar to atom sort from the last homework assignment, uh, the doing proofs on this kind of counter kind of thing, always going down, is quite tricky, and we're actually going to be forced to do induction. And I say forced, it's not really true that it's forced. There are definitely different ways to do it, but I think that one, this is a very instructive way of doing induction. So it will just make your induction skills very solid, and also, um, I think it just makes a pretty clean proof. So let's think about the main idea here. So again, when you're doing these proofs on objects of like a certain size, that are indicated that is indicated by specific numbers. So in this case, graphs with a certain number of vertices. Um, we always have to instantiate something with n plus 1 of those things, right? So okay, let me make my tree with n plus 1 things, and uh, I want to show that this tree must have uh, exactly n edges, right? N plus 1 vertices and n edges is the goal. And I get to assume that n vertices, n vert tree implies n minus 1 edges. Oops. So can someone help me think of a strategy that will allow me to go from so this has n plus 1 vertices. What am I doing? So this has n plus 1 vertices. How can I use this assumption to show that this tree must have n edges? I have less than a minute left. Okay, thank you, Max. I'm going to make a new meet. Okay, I'm putting the link in here and in Discord. I will see you momentarily. Hi everyone, welcome back. Uh, Nick, do you mind muting? You have some background noise. Thank you. Okay. Um, so let's take a look. Yeah, so anyone have any ideas for how to use this assumption to actually make some statement on this tree with n plus 1 vertices? The point is that I can only use this assumption if I have an n vertex tree, right? If I don't have an n vertex tree, then I pretty much have nothing going on here. Or I could use the contrapositive and say that if you don't have n minus 1 edges, then you can't be an n vertex tree, but that's definitely not helpful. So I need to get an n vertex tree. So what can I do? What can I do to this graph to actually get an n vertex tree? Take off a leaf. Brilliant idea. And how do I know that there's a leaf? Well, because of proposition 5.15, I know there's at least two leaves. Since we have n plus 1, we know there's at least two vertices. So we get to use proposition 5.15. And so I take off a leaf. Just ignore it. And ignore the edge too, right? So I have this thing. This has n vertices. And all of a sudden, I know that this is an n vertex tree, except I don't. It has n vertices, but I need to prove that this new thing is a tree, and you might be very frustrated because just look at it, this is obviously a tree, but unfortunately we do have to prove that this is a tree. So uh, the details are in the lecture notes, I'll get to them quickly, but just to review the intuition, so now this thing has n minus 1 edges, and now when I go back to my original thing, I'm just adding in one edge, right? So that means that this n plus 1 vertex tree has to have n edges. So yeah, you do induction, and you convert your big object into your slightly smaller object, and then by induction everything works out. So this is actually really similar to problem 5 from the last homework. With the convex polygon, you took off one vertex, you used the property, and then you added the thing back. And this is literally the same thing in terms of words, right? These are both vertices. Okay, so now let's look at the dirty details. So obviously for one vertex, this works out. You have 0 edges. Okay, so you suppose your nice property that we just assumed. You create your tree, and you take your leaf, and then you make a new graph G prime by deleting V and the single edge connected to it. So this is a little bit informal, saying deleting V, but you can take this much liberty without creating these objects very specifically. Okay. Now we need to show two things to show that this is a tree. We need to show one, it's connected, and two, it's acyclic. So let's first show that it's still connected, and this is the one that's slightly non-trivial, because for example, if I took out this vertex, right, then the resulting graph is actually not connected, right? So you definitely need to make sure that when you take out a vertex from your graph, that it's still connected. Okay, so the point is that since it's a leaf, right, if there was any path between two vertices before, then this leaf can't appear in the middle of the path, because then it would be connected to two different things on either side in the sequence, right? So um that means, I mean, the details are annoying, but that means that basically you couldn't have heard anything by taking off a leaf. Okay. Now for showing it's acyclic, this is a little bit easier because, okay, well, if there's a cycle inside of this, right, then that cycle would still exist in the big graph, and that's not possible because the big graph is a tree, right? The big graph is a tree, so it has no cycles, and so this thing can't have any cycles either, right? You can only create a cycle by adding edges, right? Removing edges is not going to add a cycle. There's no way. Okay. And so we've shown that G prime is a tree with n minus 1. Sorry. Yeah, G prime is a tree with n vertices, right? Which means it has n minus 1 edges, and like I mentioned, that means that G itself has n edges. Okay. So, barring some of the details about showing that G prime is a tree, does everyone understand the gist of how we did this induction? Or are there any questions? Oh, all good. Okay, very good. And finally, we have just one more definition, bipartite graphs. So these are actually really, really interesting objects. So okay, let's give you really I guess hairy definition. So you have a graph, so vertex at V, I've set E as always. And there are two sets A and B, such that A union B is the whole vertex set, A intersect B is the empty set, and all the edges are between vertices in A and vertices in B, but not between vertices in A and itself or B and itself. Okay, so this is not easy to imagine. So basically, it's saying that I can partition my vertices into A and B. So I have some guys here. That's a 6. I have some guys here. And I don't have edges like this or like this, ever. All my edges cross the line. So maybe something like this. And this guy doesn't need to have any edges. Okay, so this is a bipartite graph. And this shows up in a lot of cases. Just as an example, there's something known as Hall's marriage theorem. It works on bipartite graphs, and it comes from saying like, okay, what if we have a bunch of girls and a bunch of guys, all of which who are heterosexual and have preferences. So, for example, this girl is only willing to get married to these two guys. So, how many successful partnerships could you create? Right? That's what we call a matching on a bipartite graph. Um, a more practical example is okay, you have requests coming in from people trying to load a website, and you have servers that they're allowed to connect to. How do you balance the connections such that no server is too overloaded? So this is actually a really interesting problem of uh, dealing with a lot of data that's coming in real time and balancing your server load. And I don't know the theory there, but I'm sure it's really, really fun to look into. So anyways, that's where you might see bipartite graphs. And some examples. Okay, so the path graph is always bipartite. And so the way to show that is that you take your path graph, right? Boom, 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 boom. And you can just say like, okay, the first guy is going to be in A, the second guy is going to be in B. The first guy is going to be in A, and the second guy is going to be in B, and blah, blah, blah. So then you would get this thing, right? And so on. So the path graph is pretty obviously bipartite. And the star graph is bipartite. So if you recall, it's like that thing with the center, and it's connected to n different things. And that's bipartite because we can do, okay, the guy in the center is here, and everything else is connected to is here. So showing that something is not bipartite is actually kind of hard because you need to show there's no way to pick these subsets A and B such that this is possible. But for your computer scientists, you will know that BFS actually gives a really easy way to calculate directly if a graph is bipartite or not, but I will not go into that now. Okay, so you will use bipartite graphs, I believe, in some problem. Right, so we're going to talk about graph colorings in here. So this homework is hard. So you guys will have to be very careful. I do expect a lot of mistakes, but really take your time. If you can, start tonight, start early, and take your time to think about it. So 5.1 we already talked about, obviously, so just forget about that. You don't have to write anything. Just start from 5.2. And yeah, I think these problems are pretty fun, but given the fact that you guys are early on, okay, yeah. So Max says this is the hardest homework. So yeah, yeah. So take your time. I do think the problems are fun, but because it's so challenging, it might not be as fun as it should have been. But yeah. Oh, also have fun reading 5.6. It's like Among Us or something. Uh, and so I think actually I'll take a poll. And I'll see if you guys want to do like a group problem solving session on this homework. We can do that probably tomorrow. So yeah, I'll ping everyone and ask pretty soon after the lecture if you guys are interested in that. And I think that would be pretty helpful considering how hard it is. Um, yeah. Okay. Any problems before, or sorry, any questions? Any questions before we end the lecture? Okay. All right. So silliness aside in the chat. All right. Thank you everyone for coming and have a great day. Bye bye.